Good morning, everybody. Every time I get something like this in the shop, it never comes with a schematic. And we go through our basic short circuit test. And if we find nothing wrong, nothing that we have to replace, we've got to figure out how to power this thing up. This is a power supply right here. It's going to take a input voltage, an AC input voltage or a DC input voltage, depending on what you got on your bench, and it's going to output a voltage. So how do you figure out, without a schematic, without the machine wrapped around this thing to where you can plug it into the wall, how do you figure out how to power this up on your bench? Well, in this instance right here, let's take a look, see how. The first place I like to start looking to determine the amplitude of the voltage coming into this board is the filter capacitor. This right here is the filter capacitor. It'll have a value and a voltage rating on the side of the package. Now here we have 1000 microfarad at 50 volts. Now, if this capacitor is filtering the incoming voltage, whether it be AC or DC, it cannot be greater than that 50 volts that's written on the side of this filter capacitor. If we exceed that 50 volts, we're going to blow this cap. This cap will explode. So we know if this is the filter capacitor, and we'll work it back into the circuit in Scotia bit. But if this is the filter capacitor for the power supply, the incoming voltage cannot be greater than 50 volts. So let's work it back into the circuit and see how that's tied in. Draw that filter capacitor first. Draw it out here on the end. (1000 microfarads, 50 volts, and the board says that's C6, so let's draw its location on the board, C6, in our diagram. Okay, here's the positive side. We'll work with that first. Looks like it comes back into these rectifying diodes right here. Okay, there's cathode to cathode. Let's draw that in. Whenever you see 4 diodes on a board like that, you can make the assumption that this is a bridge rectifier. Anode to anode. The anode to anode goes to the bottom, the negative side of the bus capacitor. So we'll draw our little bus ground symbol right there to indicate that this is bus ground of the power supply, and these 2 points right here are connected together. Now, let's find out where the input to the bridge rectifier comes from. we're working our way back. Okay, let me show you what I've got so far. Here's the big blue bus capacitor. Here's the 4 rectifying diodes. These 2 points right here indicate bus ground, and they're tied together. What we're going to do now is find out where the input to the bridge rectifier comes from. We're not worried about that side yet. We're worried about bringing the voltage in. Okay. Put your meter in beep mode. We'll check our continuity. We can eyeball it too. Looks like we have an MOV right there. MOV from pin 1. Dig through that conformal coating. Is that an MOV or an inrush? Okay, that's an inrush. Inrush slows the incoming current, so we don't have a huge surge to charge up this big bus capacitor right here. So we have an inrush. Now where does the inrush go? It's going to have to go to one of these right here. Let's see if they're tied together. Yes, these two are tied together. These two are tied together. Okay, the inrush. Call that. Draw a little picture of an inrush. In rush. That goes to pin 1 of this Phoenix connector right here, this green connector. Let's bring that back out here. Call that pin 1. Now, how about the other side? The other side of the bridge rectifier right here goes to pin 2, so we'll bring this out, show it going to pin 2. Now there's some filtering going on here. It looks like they go to frame ground. Let's see how that's tied in. Okay. Looks like it's tied to, let me get my big glasses on here, my close-up glasses. Looks like it's tied to frame ground. Here's frame ground right here. Yes. Okay. Okay, then there's an MOV right here. So we have a filter. Let me draw that in here. It goes to frame ground. We have a filter down here. It also goes to frame ground. Now what you have in these filters, you have capacitance and inductance, and the capacitors and inductors filter the line noise. Okay. And then we have an MOV right here. It's MOV6. This is EMI filter 1. And this one over here is EMI filter 2. Here's our Phoenix connector. It's called J1. Okay, let's look at the other side, see if there's anything connected here. See, it looks like pin 3 and pin 4 are not connected, but pin 5 is connected to frame ground. Okay, so we'll draw that in. Three, 4. No connect, NC for no connect. And pin 5 is frame ground. Okay. So down here, let's see. Show you close up of the EMI filters. These little brown things are the EMI filters. There's a capacitor and a couple of inductors in there to make a pi filter. This right here is the MOV. That's across pins 1 and 2 of this connector. And right here is the inrush. Now the purpose of the MOV, that's a metal oxide varistor. It has high resistance until its rating is exceeded. If we overvolt that MOV, it shorts. And most of the time you'll see these exploded open because of the short circuit energy. But what it does, it gives up its life. It gives up its life to save the rest of the circuit. That's the purpose of that MOV. Let me set up the circuit to power this up. We'll see if we can bring it up. Hey, we're back. Okay, let me show you what we got drawn out so far on the AC input to this power supply. There you go. Pins 1 and 2 are the AC input to this power supply card. We have filtering to filter out the line noise. We have current limiting by this inrush to current limit the inrush surge of our filter capacitor here. We have the 4 diodes that make the DC voltage. They convert the AC coming in to DC going out. Now, we're ready to fire this thing up. I've got a variac right now set to 0 volts because I'm not sure what the minimum voltage is into this power supply, so we're going to sneak up on it with this variac. The thing that you have absolutely cannot do is exceed the voltage rating of this capacitor when we up this AC voltage coming in. So we are going to find a place where we can look at that DC voltage across that capacitor. That would be ground right there, and that would be positive right there. I got to dig through the conformal coating. Let's see if we made it. Nope, not yet. There we go. Okay, now we have, dig hard through that conformal coating. Let me turn this light on so you can see that voltage. I've got 8.21 volts DC across this bus capacitor. I'm looking on the bridge rectifiers, positive and ground. So we'll increase that. Okay, there's 25 volts DC, 26.03 volts DC right there. And our power on LED and our plus 12 volts LED has come on. Let's go look, see what voltage, AC voltage, was required to make that DC voltage. I got 20.19 volts AC on pins 1 and 2, and that gave me 26.07 volts DC. All right. So we had 20 volts AC here and 26 volts DC there. Let's measure some of our DC voltages. Okay, there's the 12 volt connector, J2, and I have 11.95 volts DC there. Let's look at some of these ICs over here, see what voltage we've got there. Dig through that conformal coating. Okay, across that PAL, programmable array logic, I've got 5.01 volts DC. There's some other voltages we can check, but so far everything looks good. There you go. Hope you enjoyed that video. That's how you figure out the incoming AC voltage of any circuit that you're working on. This one happens to be a power supply. So we've got AC in here, gets converted to DC over here. And from our diagram, we know that the incoming AC cannot make a voltage. We cannot make a voltage that exceeds the bus capacitor voltage rating. So we know that our AC in coming in is not going to be very large because this bus capacitor right here is only 50 volts. So look at this capacitor right here. This capacitor will tell you what the incoming line voltage is. Thank you very much for watching. At the end of the video, I'll put some math up on how to calculate a voltage here from a voltage here. Evening all. Here we are again. It's been a couple of days since I got to the end of the last video there, and I wanted to explain to you how we figure out the AC voltage coming in based upon the filter capacitor here. What equation can I use to determine the AC voltage coming in rectified here with the bridge rectifier, and filtered with this capacitor right here. Now this is the circuit from the power supply board that I had worked out a couple of days ago. So let me show you that equation. Let's move that out of the way. This right here is the relationship between the peak sine wave and the effective voltage. We have the peak sine wave, E max, is equal to the effective voltage times the square root of 2. Now the square root of 2, sometimes you'll see 0.707. 0.707 is 1 divided by the square root of 2 will equal 0.707. What is the effective voltage? Well, the effective voltage is the value of an AC voltage that is equally effective as a corresponding DC voltage. And for a sinusoidal AC voltage, the effective voltage is equal to 0.707 of the peak sine wave voltage. And this is also called the RMS voltage. Well, how can we use this equation right here to determine the AC voltage coming into that power supply circuit? We're going to do a little bit of changing of words here. It's the same equation with different words. Voltage across the capacitor, that's the filter capacitor in that drawing, is equal to VAC, voltage alternating current, the sine wave, max input times the square root of 2. It's the same. It is the same equation as this up here, but with different words. Okay, so let me put this back up in here. Here's the voltage across the capacitor is equal to VAC max input right here, where we're going to put our AC input, times the square root of 2. Let's do a little bit of transposing. We want to know what the maximum AC input to that circuit is, so we divide both sides by the square root of 2. I'm reaching over the camera here, so my handwriting is going to be a little bit sloppy. Okay, that cancels this out. Square root of 2 divided by the square root of 2 is 1, so that would be VAC max in times 1, so that cancels out. So the AC maximum input to that circuit is equal to the voltage across the capacitor divided by the square root of 2. In our example, let's bring that back into the circuit. Let me move down a little bit here, and we'll bring our circuit back into play. Here we go. This is the voltage across the capacitor is 50 volts DC, divided by the square root of 2 gives us a maximum AC voltage coming into this circuit of 35.36 volts AC. So if we were to put 35.36 volts AC on pins 1 and 2, it would be rectified, and we would have 50 volts across this capacitor right here. And that would be putting us right on the edge of the maximum voltage rating for that capacitor. So you cannot put that voltage on there, but that gives us an upper limit with which to work with. Now here in America, most of our voltages are 24 volts AC, 120 volts AC, 220 volts AC, and 380 volts AC, 400 volts AC, 460 volts AC, and every now and then, once in a blue moon, we see 575 volts AC. But we know that we cannot put anything greater than 35.36 volts AC into this power supply right here, because we would blow that cap. That cap would explode because we reached its maximum voltage rating of 50 volts. So what are we going to put in there? Well, the closest here in America is 24 volts AC. At 24 volts AC, pull out the old calculator. 24 volts AC times the square root of 2, or 1 over the square root of 2, gives us DC voltage across that bus capacitor of 33.94 volts DC. So that's where I would start. I'd start with the 24 volts AC. And if the power supply comes up with 24 volts AC, well, we're good to go. That's all we need to do. Let's work out a couple of other of these different voltages that we have that we can experiment with here. Give me a little bit to set the paper up, and I'll come back in a little bit. Okay, here's another example. Let's say our filter capacitor out here is 1000 microfarad at 250 volts. Well, we can't exceed that 250 volts without blowing that capacitor. That cap will explode. So how much AC voltage can I put in to this circuit here, the bridge rectifier and the filter capacitor, before we reach that 250 volt limit? Well, here we have 250 volts divided by the square root of 2. That gives us 176.8 volts AC, at which point we reach that 250 volt DC limit. Well, that tells us we can't put that in here, but what do we put in here? What is the closest value that's available here that we could put in to that circuit right there? Well, 120 volts AC would be the closest value here in America that we could put into this rectifier, bridge rectifier, filter capacitor circuit without reaching that limit. Well, if we did put 120 volts AC in, what voltage will we have across that capacitor? Let's take a look. Let's pull out the old calculator and let's do 120 volts AC times the square root of 2. Plug that into the calculator, and that gives us, don't know if you can see it there, that gives us a value of 169.7 volts across that capacitor. That's well under the max voltage rating of 250 volts for that capacitor. And that right there is how you determine the incoming line voltage for that power supply based upon this filter capacitor, the bridge rectifier circuit. Would you like to try another example? Let me put another one up there. We'll do one more. Okay, in this circuit we have a 1000 microfarad 800 volt capacitor filtering the output of this bridge rectifier. To determine the incoming line voltage, we use this equation right here. 800 volts divided by the square root of 2 gives us 565.7 volts AC. The AC, 565.7 volts AC right here will make 800 volts DC right there after it's rectified with the bridge rectifier. That tells us that we cannot put 565 volts AC into this circuit without getting right on the edge of that voltage rating for that capacitor. And any kind of surge on the line which brings this AC up, the DC will go up, will exceed that 800 volts, and we'll blow that cap in a heartbeat, and that capacitor will not live for very long. So what voltage, what AC line voltage do we put into this circuit so that we don't get close to that 800 volts? Well, here in America, the next lowest value to 565.7 volts AC is 460 volts AC. We could put that in there with not exceeding that capacitor right there. Let's see what DC voltage we would have on this circuit if we put 460 volts AC in. What would be the voltage across that capacitor? Well, we do 460 volts AC times the square root of 2 will give us that voltage across that capacitor. Let's fire up the calculator. We have 460 volts AC times the square root of 2. That gives us 650.5 volts DC across that capacitor. That's well under the 800 volts DC. So we could have 460 line in, 650.5 volts DC right here, and we would not pop that cap right there. So that's how you figure it out. Going from an unknown to a known, let the board tell you what this incoming line voltage is right here. That board has all the parts to tell us what we need to know. One thing I need to say here about power supplies and powering up circuits with unknown voltages that you're not sure about the input voltage here. If you're worried, if it bothers you to straight out, say for instance in this circuit, if it worries you about putting 460 volts AC into the circuit right off the bat, there's a couple of things you can do. You can sneak up on it with a variac, plug the output of a variac into this power supply circuit right here, and gradually bring up the voltage until the power supply fires up. That's a trick that I highly recommend. Throwing 460 volts AC at a circuit like this, even though we know we won't exceed that bus cap, that's a scary thought. Very scary thought. I can't tell you how many times I've been worried about firing up something in the shop when I didn't know how much voltage was going into it. If you can, find a manual, a PDF manual online on the unit that you're working on. You can even go back to the customer and say, hey, I got your board in. I don't know how much volts to put in on pins 1 and 2 of J1. Can you go find out for me? And 10 times out of 10, they'll call you back and they'll say, hey, Mac, it's 460. Okay, thank you. And just different ways to find out one way or the other if it worries you about putting these high voltages into a power supply circuit like that. It worries me, I'm not kidding you. It bugs the dog out of me when I've got to fire up something and I don't know how much AC to voltage to put in there. This right here will give you a good benchmark. You don't want to exceed this filter capacitor right here. It'll tell you that you've got to be below this voltage right here. But what is the minimum? Let's say, for instance, the manufacturer stuck an 800 volt cap out there, but the rest of the circuit only wants 120 VAC coming in, which would give you 170 volts DC right here. Well, that's where this intuition and calling up the customer and asking them, looking for a PDF manual, whatever it takes, using a variac to come into it, whatever it takes for you to power up this power supply to make sure it's functioning. Alright folks, it's getting dark outside. I got to do some laundry before I can get up and go back to work. Thank you very much for watching. I hope that you enjoyed that video, and come back anytime. It's always good to have you come over. Enjoy the time with your family. We'll see you next time.